Right now, as you sit here, as you breathe, as your heart beats, light is traveling through space at a speed your mind cannot truly grasp. It moves at 299,792 kilometers every single second. In 1 second, a beam of light could circle the entire Earth 7.5 times. In 1 minute, that same beam would travel roughly 18 million kilometers. In 1 hour, it would reach beyond the orbit of Jupiter. And in 1 full year, that tireless beam of light, traveling at the fastest speed the universe allows, would cover approximately 9.46 trillion kilometers. That distance, that unfathomable stretch of empty space, is what scientists call a single light year. And the nearest world that might, just might, be capable of supporting life as we know it is not 1 light year away. It is not 2, it is not 3, it is 4.24 light years away. That translates to roughly 40 trillion kilometers. 40 trillion. Let that number sit in your mind for a moment. 40, followed by 12 zeros. 40,000 billion kilometers of almost perfect vacuum, of silent emptiness, of cold, dark nothingness, stretching between you and the closest place beyond Earth, where water might flow, where air might exist, where something alive might look up at its own alien sky. And here is what makes this distance truly terrifying. Humanity's fastest spacecraft, the object we have flung hardest and fastest into the void, is Voyager 1. It was launched on September 5th, 1977. It has been traveling through space for nearly 49 years. It is currently approximately 172.6 astronomical units from Earth, which is about 25.8 billion kilometers. That sounds impressive until you realize that the distance to our nearest potentially habitable neighbor is roughly 40 trillion kilometers. Voyager 1 has covered, in nearly half a century of flight, approximately 0.064% of that distance. Less than 1/10 of 1%. At its current speed of about 17 kilometers per second, Voyager 1 would need more than 73,000 years to travel the distance to Proxima Centauri. 73,000 years. Human civilization as we know it, with agriculture and cities and written language, is roughly 10 to 12,000 years old. We would need to survive as a species for 6 or 7 times longer than all of recorded civilization just for Voyager 1 to crawl across that gap. And Voyager 1 is not even heading in the right direction. So the question becomes impossibly fascinating. What is this world, this nearest potentially habitable planet? What do we actually know about it? How did we find it? What is the star it orbits? What are the chances it could actually harbor life? And most haunting of all, will any human being in any generation ever set foot on its surface, or even send a machine to photograph it up close? These are the questions we are going to explore together, and the answers are going to challenge everything you think you know about space, distance, technology, and the future of our species. Because the truth is that the universe has placed a potentially habitable world tantalizingly close to us, closer than any other in the cosmos. And yet, it might as well be on the other side of the universe for all our ability to reach it. Before we go further, if you love deep explorations of space and science, if you want to understand the cosmos not through hype and sensationalism, but through real, verified, breathtaking facts, then subscribe to this channel right now, hit the like button, and drop a comment telling me what you think is the biggest obstacle standing between humanity and the stars. Is it distance? Is it energy? Is it time? Or is it something we have not even considered yet? I read every single comment, and your perspective might be exactly the insight someone else needs to hear. Now, let us begin this journey from the very beginning, from right here on Earth, and travel outward step by step until we reach the doorstep of the nearest world that might welcome life. To truly understand how far away the nearest habitable world is, we first need to build an intuitive understanding of cosmic distances, because the numbers involved are so large that they lose all meaning unless we anchor them to something familiar. So let us start small and work our way out. The Moon is the closest celestial body to Earth. It orbits at an average distance of about 384,400 kilometers. When the Apollo astronauts traveled to the Moon, it took them about 3 days to get there. That is a distance your mind can still handle. You can imagine 3 days of travel. You have experienced 3 days. The moon feels close, and in cosmic terms, it is absurdly close. It is right next door. It is practically touching us. Now consider the sun. It is approximately 150 million kilometers from Earth. Light covers that distance in about 8 minutes and 20 seconds. So when you look at the sun, you are seeing it as it was 8 minutes ago. If the sun suddenly vanished, you would not know for 8 minutes. That distance, 150 million kilometers, is called 1 astronomical unit, or AU. It is the basic measuring stick of our solar system. The sun feels far away, and for human scales, it is. But in the context of what we are about to discuss, it is nothing. It is a grain of sand on a beach that stretches across continents. Mars, at its closest approach to Earth, is about 55 million kilometers away. At its farthest, it is over 400 million kilometers away. Our robotic missions to Mars take roughly 7 to 9 months to arrive. Jupiter is about 5.2 AU from the Sun, roughly 778 million kilometers. Saturn is 9.5 astronomium. Uranus is 19.2 astronomium. Neptune is 30 astronomium. And Pluto, that tiny icy world at the edge of the classical solar system, orbits at an average distance of about 39.5 AU2, which is approximately 5.9 billion kilometers from the Sun. The New Horizons spacecraft, which was launched in January 2006 at one of the fastest launch speeds ever achieved by a human-made object, approximately 58,500 kilometers per hour, took 9.5 years to reach Pluto. 9.5 years of hurtling through space at blistering speed to reach a world still within our own solar system. Now here is where things get uncomfortable. 1 light year is approximately 63,241 astronomical units. Proxima Centauri, the nearest star to our Sun, is at a distance of about 268,778 years. To travel from Earth to Proxima Centauri, you would need to cover a distance equivalent to going from Earth to the Sun approximately 268,000 times, or going from Earth to the Moon roughly 104 million times, or driving a car at highway speed 120 kilometers per hour, 24 hours a day, 7 days a week, for approximately 38 million years. Let that land. 38 million years of non-stop highway driving. The dinosaurs went extinct 66 million years ago. You would need to drive for more than half the time since the dinosaurs disappeared just to reach the nearest star. Let us try another way to feel this distance. Imagine you could shrink the entire Earth down to the size of a marble, about 1 centimeter in diameter. On this scale, the Moon would be a tiny speck about 30 centimeters away, roughly the length of a ruler. The Sun would be a ball about the size of a large beach ball, sitting about 117 meters away. Mars, at its closest, would be about 43 meters from Earth. Jupiter would be about 600 meters away. Neptune would be about 3.5 kilometers away. And Pluto would be roughly 4.5 kilometers from the Sun. That is our solar system on this scale. Everything from the Sun to Pluto fits within a circle about 9 kilometers across. Now, on this same scale, where would the nearest star be? Proxima Centauri would be approximately 31,000 kilometers away. 31,000 kilometers. That is roughly the circumference of the Earth. So, on a scale where our entire solar system from the Sun to Pluto fits within a small city, the nearest star is on the other side of the planet. The emptiness between stars is staggering beyond words. And that emptiness is not entirely empty, though it might as well be. The space between stars is filled with what scientists call the interstellar medium, a fantastically thin soup of hydrogen gas, dust particles, cosmic rays, and weak magnetic fields. But when I say thin, I mean thin beyond anything you have ever encountered. In the region near our Sun, the interstellar medium contains roughly 0.1 to 1 atom per cubic centimeter. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. That is, 25 followed by 18 zeros. The interstellar medium is, by any earthly standard, a near-perfect vacuum. It is emptier than any vacuum we can create in a laboratory on Earth. And yet, as we will discover later, even this incredibly sparse medium becomes a serious problem if you try to cross it at very high speeds. Now that you have some sense of the scale we are dealing with, let us turn our attention to the star at the center of this story, Proxima Centauri, the closest star to our Sun, and immediately there is something strange and humbling about it. Despite being the nearest star to Earth, you cannot see Proxima Centauri with your naked eyes. Not even on the clearest, darkest night, from the most remote location on Earth, with perfect eyesight and zero light pollution. It is simply too faint. Its apparent visual magnitude is about 11.13, which means you need at least a small telescope to detect it at all. The nearest star to our home world, and it is invisible to us without technology. Proxima Centauri is a red dwarf star classified as spectral type M5.5V. This makes it one of the smallest and coolest types of stars that exist on the main sequence, the category of stars that are actively fusing hydrogen into helium in their cores. It has a mass of only about 12.2% of our Sun's mass, and a radius of only about 15.4% of the Sun's radius. If you could place Proxima Centauri next to the Sun, it would look like a dim ember sitting next to a bonfire. Its effective surface temperature is approximately 3050 Kelvin, compared to the Sun's 5778 Kelvin, and its luminosity is just 0.17% of the Sun's total energy output. In visible light, the kind of light your eyes can see, Proxima Centauri emits only 0.005% of what the Sun produces. Most of its energy is radiated as infrared light, invisible to human eyes. It is a dim, cool, faint little star. But do not let its small size fool you into thinking Proxima Centauri is peaceful. It is one of the most violent stars in our immediate neighborhood. Proxima Centauri is what astronomers call a flare star. It undergoes sudden, unpredictable eruptions where its brightness can increase by a factor of 100 or more within just minutes. These stellar flares release enormous amounts of ultraviolet radiation, X-rays, and charged particles in events that are, relative to the star's size, far more energetic than anything our Sun produces. Observations with the ALMA Observatory, the Atacama Large Millimeter and Submillimeter Array, have revealed extreme flaring activity at radio and millimeter wavelengths. The star's magnetic field is extraordinarily powerful, approximately 600 Gauss, compared to the Sun's general magnetic field of about 1 Gauss, and it varies in a roughly 7-year cycle. This intense magnetic activity drives the constant flaring, and as we will see, it poses one of the most serious threats to the habitability of any planet orbiting this star. But here is something remarkable about red dwarf stars like Proxima Centauri that makes them cosmically significant. They are incredibly long-lived. Our Sun, a G-type main sequence star, has a total lifespan of about 10 billion years. It is currently about 4.6 billion years old, roughly halfway through its life. When our Sun dies, it will swell into a red giant, engulf the inner planets, and eventually shed its outer layers to become a white dwarf. Proxima Centauri, because it is so small and burns its fuel so slowly, has a projected lifespan of potentially 4 trillion years or more. That is not a typo. Trillions of years. The universe itself is only 13.8 billion years old. Proxima Centauri has barely begun its life. It will still be shining, still burning hydrogen, long after our Sun has died, long after most of the stars you can see in the night sky have burned out. If there is life on any planet orbiting Proxima Centauri, it has an almost incomprehensible amount of time to develop. Evolution on Earth has had about 4 billion years. A planet around Proxima Centauri could have trillions of years. And red dwarfs like Proxima Centauri are not rare. They are, in fact, by far the most common type of star in the Milky Way galaxy. Roughly 70 to 75% of all stars in our galaxy are red dwarfs. They are everywhere. Most of the stars nearest to our Sun are red dwarfs. And because planets are extremely common around red dwarfs, with on average 1 to 2 planets per star, and because about 20 to 40% of red dwarfs have at least one planet in their habitable zone, there could be tens of billions of potentially habitable planets orbiting red dwarfs in our galaxy alone. The cosmos may be absolutely teeming with worlds like the one we are about to explore. Proxima Centauri is not a solitary star. It is part of a triple star system called Alpha Centauri. The system's other 2 members are Alpha Centauri A and Alpha Centauri B, which form a binary pair orbiting each other. Alpha Centauri A is a G2 V-type star, remarkably similar to our Sun in size, temperature, and luminosity. It has a mass of about 1.1 solar masses and is slightly brighter than the Sun. Alpha Centauri B is a K1 V-type star, a bit smaller and cooler than the Sun, with a mass of about 0.9 solar masses and an orange hue. These two stars orbit each other with a period of approximately 79.9 years, and their separation varies from about 11.2 astronomical units to 35.6, comparable to the distances of Saturn to Neptune from our Sun. The binary pair of Alpha Centauri A and B lies at a distance of 4.344 light-years from Earth. Proxima Centauri orbits this binary pair at an immense distance, approximately 13,000 astronomical units, which is about 0.2 light-years from Alpha Centauri A and B. Its orbital period around the binary pair is estimated at roughly 547,000 years. Because of its slightly closer position to our solar system compared to the AB pair, Proxima Centauri is the closest star to the Sun at 4.2465 light-years. It is possible that Proxima Centauri was not born together with Alpha Centauri A and B, but was instead captured by their gravitational influence later, though this remains debated. The Alpha Centauri system, because of its proximity and the Sun-like nature of its brightest member, has been a source of fascination and speculation for centuries. But it was not until August 24, 2016, that the system leaped from astronomical curiosity to the center of one of the most significant scientific announcements of the 21st century. On that date, a team of astronomers led by Guillaume Anglada Escudé at Queen Mary University of London announced that they had discovered a planet orbiting within the habitable zone of Proxima Centauri. The planet was named Proxima Centauri B, or simply Proxima B. It was found using the radial velocity method, also known as Doppler spectroscopy, through observations made with instruments at the European Southern Observatory in Chile. The announcement was published in the journal Nature, and it sent shockwaves through the scientific community and the general public. The nearest star to our Sun had a planet in its habitable zone. A potentially habitable world was right next door, cosmically speaking. But the discovery did not happen overnight. It was the result of years of painstaking work. Astronomers had been searching for planets around Proxima Centauri for over a decade before the discovery of Proxima B. Studies published in 2008 and 2009 had ruled out the existence of any planets larger than Earth in the habitable zone, but those studies were limited by the sensitivity of the instruments available at the time. As instruments improved and more data accumulated, subtle anomalies began to emerge in the motion of Proxima Centauri. The star appeared to be wobbling ever so slightly, in a pattern that could not be explained by stellar flares or chromospheric activity. Something was tugging on it gravitationally. Something with the mass of a planet. To understand how this discovery was made, you need to understand the radial velocity method in some detail, because it is one of the most elegant and precise techniques in all of science. When a planet orbits a star, it does not simply go around the star while the star stays still. Both the planet and the star orbit their common center of mass. Because the star is much more massive than the planet, this center of mass is usually located inside the star, very close to the star's center. But the star does move. It wobbles, it sways back and forth in a tiny orbit, pulled by the planet's gravity. Now, when the star moves toward Earth in its wobble, the light it emits is very slightly compressed, shifting toward the blue end of the spectrum. When it moves away, the light is stretched, shifting toward the red end. This is the Doppler effect, the same phenomenon that causes a siren to sound higher pitched as an ambulance approaches and lower pitched as it drives away. By measuring these incredibly tiny shifts in the star's light with extraordinary precision, astronomers can determine that a planet exists, estimate its minimum mass, calculate its orbital period, and determine its distance from the star. The wobble caused by Proxima B on Proxima Centauri has a semi-amplitude of only about 1.226 meters per second. That is slower than a person walking at a casual pace. The star is moving back and forth at a speed of about 1 meter per second because of this planet's gravitational pull, and astronomers detected this from 4.2 light-years away. The precision required to measure this is mind-boggling. It is equivalent to measuring the width of a human hair from thousands of kilometers away. In January 2016, to confirm the signals hinted at by earlier observations, the team launched a dedicated observing campaign called the Pale Red Dot Project. Over several months, they gathered intensely focused observations using the HARPS spectrograph at the European Southern Observatory's 3.6-meter telescope in La Silla, Chile, along with supporting observations from other facilities. The data confirmed what the preliminary signals had suggested. There was a planet there, and it was in the habitable zone. On August 24, 2016, the discovery was made public, and Proxima Centauri b instantly became one of the most famous exoplanets in the world. As of recent surveys, it is believed to be the best-known exoplanet among the general public. Now, let us explore what we actually know about this world. And I want to be very careful here, because in the excitement surrounding this discovery, there has been a great deal of speculation and hype. I am going to stick strictly to what the science tells us, what is confirmed, what is estimated with reasonable confidence, and what remains genuinely unknown. Proxima Centauri b has a minimum mass of approximately 1.055 Earth masses, with an uncertainty of plus or minus 0.055 Earth masses. This measurement was refined in a 2025 study. The word minimum is critically important here. Because the planet was detected using the radial velocity method, we can only measure the component of the star's wobble along our line of sight. If the planet's orbit is tilted relative to our viewing angle, the actual mass could be higher. The true mass depends on the orbital inclination. If the inclination is about 47 degrees coplanar with the rotation axis of Proxima Centauri, the true mass would be approximately 1.44 Earth masses. So Proxima b is either very close to Earth's mass, or somewhat heavier, but it is in the range that astronomers consider likely to be a rocky terrestrial planet, rather than a gaseous one. The radius of Proxima Centauri b has not been directly measured. The planet does not transit its star as seen from Earth, meaning it does not pass between Proxima Centauri and us during its orbit. Without a transit measurement, we cannot determine the radius directly. However, based on models of possible compositions, the radius is estimated to range from about 0.94 to 1.4 Earth radii. This is a significant uncertainty. At the lower end, Proxima b would be slightly smaller than Earth. At the upper end, it would be noticeably larger. The composition is similarly uncertain. Depending on what the planet is made of, it could range from a Mercury-like world with a large iron core and thin mantle to a water-rich world with a substantial fraction of its mass being water or ice. Observations of the iron, silicon, and magnesium ratios in Proxima Centauri's spectrum suggest they are similar to our Sun's ratios, which in turn suggests that any rocky planet formed from this material might have a broadly Earth-like composition. But this is an inference, not a measurement. Proxima b orbits its star at a distance of approximately 0.04848 astronomical units, which translates to about 7.25 million kilometers. To put this in perspective, Mercury, the closest planet to our Sun, orbits at about 0.39 AU. Proxima b is roughly 8 times closer to its star than Mercury is to the Sun. It orbits more than 20 times closer to Proxima Centauri than Earth orbits the Sun. Because of this extreme proximity, Proxima b completes one full orbit, one full year, in just 11.186 Earth days. A year on Proxima b is less than 12 days long. You could celebrate your birthday, wait less than 2 weeks, and celebrate it again. Despite orbiting so close to its star, Proxima b is within the habitable zone because Proxima Centauri is so dim. The habitable zone of a star is the region where temperatures are right for liquid water to potentially exist on a planet's surface, assuming the planet has a suitable atmosphere. Because Proxima Centauri produces only about 0.17% of the Sun's total energy output, its habitable zone is much closer in than the Sun's. Proxima b receives about 65% of the irradiation that Earth receives from the Sun. Its equilibrium temperature, calculated without any atmospheric effects, is approximately 234 Kelvin, which is minus 39 degrees Celsius or minus 38 degrees Fahrenheit. That is below the freezing point of water. However, this does not necessarily mean the planet is frozen. Earth's equilibrium temperature, calculated the same way, would be about minus 18 degrees Celsius, well below freezing. But Earth's atmosphere, through the greenhouse effect, raises the actual average surface temperature to about plus 15 degrees Celsius, an increase of 33 degrees. If Proxima b has a suitable atmosphere with greenhouse gases like carbon dioxide or water vapor, its surface temperature could similarly be raised above freezing, potentially into a range where liquid water could exist. But the word if carries enormous weight. Whether Proxima Centauri b has an atmosphere is the single most important unknown about this planet, and as of our current knowledge, we simply do not know. The presence or absence of an atmosphere determines everything. It determines whether the planet can have liquid water, whether it can maintain stable temperatures, whether it can shield its surface from the deadly radiation of its host star, and ultimately, whether it could ever support life. Without an atmosphere, Proxima b would be a dead, barren, irradiated rock, with temperatures permanently below freezing. With the right atmosphere, it could potentially be a world with oceans, clouds, and conditions suitable for biology. There are two broad scenarios for Proxima b's atmospheric history, and understanding them requires understanding the violent early life of this planet and its relationship with its ferocious host star. In the first scenario, which is the more pessimistic one, Proxima b formed close to its star or migrated inward early in its history. During the early stages of Proxima Centauri's life, the star was much more luminous than it is today. Red dwarf stars take a very long time to settle onto the main sequence, and during their contraction phase, they can be significantly brighter, potentially pushing any close orbiting planet beyond the inner edge of the habitable zone. This means that for perhaps the first 100 million to several hundred million years of Proxima b's existence, the planet may have experienced a runaway greenhouse effect, similar to what happened on Venus. Surface water, if any existed, would have evaporated into the atmosphere, been broken apart by ultraviolet radiation into hydrogen and oxygen, with the lightweight hydrogen escaping into space. Over hundreds of millions of years, all the water could have been lost this way, leaving behind a dry planet, with a thick oxygen atmosphere, a thin carbon dioxide atmosphere, or no significant atmosphere at all, combined with the intense and ongoing flare activity of Proxima Centauri, which would continuously strip atmospheric molecules, especially lighter ones. This scenario paints a bleak picture of a world that lost its chance at habitability very early in its life. In the second scenario, which is more optimistic, Proxima b formed farther from the star and migrated inward later, or it formed from volatile-rich material that gave it a substantial water inventory, much more than Earth's. In this case, even if the early intense phase of the star evaporated much of the surface water, there would have been enough to survive the loss. As the star dimmed and settled onto the main sequence, the planet would have entered the habitable zone with water remaining. A thick atmosphere of carbon dioxide and nitrogen, similar to early Earth's atmosphere, could have built up through volcanic outgassing, and could have been stable enough to resist the star's flaring over billions of years. Heavier atmospheric molecules like carbon dioxide and nitrogen are much harder to strip than hydrogen and helium, especially if the planet has a magnetic field that deflects charged particles from stellar flares. The truth is that we do not know which scenario played out. It could be either one or something in between. The answer hinges on factors we cannot currently measure: the planet's initial water content, its geological history, whether it has a magnetic field, the exact intensity and frequency of stellar flares over billions of years, and whether the planet formed in place or migrated. Each of these unknowns is a research field unto itself, and resolving them for a world 4.24 light-years away is one of the great challenges of modern astronomy. There is one more critical physical property of Proxima b that profoundly affects its potential habitability, and it concerns how the planet rotates. Because Proxima b orbits so close to its star, it is very likely tidally locked. Tidal locking is a gravitational phenomenon where the rotational period of a body matches its orbital period, causing the same face to always point toward the object it orbits. You are already familiar with tidal locking because the moon is tidally locked to Earth. The same side of the moon always faces us. We never see the far side from Earth without spacecraft. In the same way, Proxima b likely has one hemisphere permanently facing its star, bathed in constant reddish light, and one hemisphere permanently facing away, locked in eternal darkness. This has dramatic implications. The day side, the hemisphere that perpetually faces Proxima Centauri would receive all of the star's energy. Depending on atmospheric conditions, this side could potentially be warm enough for liquid water. The substellar point, the spot on the surface where the star is directly overhead, would receive the most energy. The night side, the hemisphere facing away from the star, would receive no direct starlight at all. Without efficient heat transport, this side would be extremely cold, potentially cold enough to freeze any atmosphere that drifted over from the day side, a process called atmospheric collapse. If the atmosphere froze out on the night side, the planet would lose its protective blanket, and habitability would be impossible. However, climate models have shown that this nightmare scenario is not inevitable. If Proxima b has a sufficiently thick atmosphere, strong winds would develop that transport heat from the day side to the night side, preventing atmospheric collapse and moderating temperatures across the planet. General circulation models, the same types of sophisticated computer simulations used to study Earth's climate, have been applied to Proxima b, and they produce a range of possible outcomes. Some models show an eyeball planet where a circular area of open ocean exists on the day side, centered on the substellar point, surrounded by a vast ring of ice covering the rest of the planet. Other models show lobster-shaped warm regions near the equator, where heat transport creates two nearly identical warm zones on each hemisphere sprouting from the equator. Still, other models suggest a global ocean is possible if the atmosphere is thick enough, or a subsurface ocean beneath a thin ice shell heated by tidal forces or internal radioactive decay, similar to what scientists believe exists on Jupiter's moon Europa or Saturn's moon Enceladus. There is also the possibility that Proxima b is not tidally locked at all. If the planet has even a modest orbital eccentricity greater than about 0.06 to 0.1, it might instead be captured in a 3-to-2 spin-orbit resonance, similar to Mercury in our own solar system. In this configuration, the planet would rotate 3 times for every 2 orbits, giving the entire surface some exposure to starlight over time. Higher-order resonances like 2-to-1 are also possible. The presence of other planets in the system, or gravitational interactions with the distant Alpha Centauri AB binary, could excite higher eccentricities. If the planet is not perfectly spherical, a non-mocked orbit could be possible even with low eccentricity. A non-mocked orbit would distribute heat more evenly, but would also cause tidal heating of the planet's interior as the gravitational forces flex and squeeze its mantle, potentially increasing volcanic activity and affecting whether the planet can maintain a magnetic field. Now, imagine standing on the surface of Proxima Centauri b, assuming it has an atmosphere you can breathe, which is an enormous assumption. What would you see? Above you, the star Proxima Centauri would appear as a dim, deep red orb, much larger in the sky than the Sun appears from Earth. Its angular diameter would be about 96 arc-minutes, roughly 3 times wider than the Sun's 32 arc-minutes as seen from Earth. But despite being larger in the sky, it would be incomparably dimmer. The landscape around you would be bathed in a perpetual, dim, reddish light, something like a permanent deep sunset on Earth, but redder and darker. If the planet is tidally locked, this star would never move. It would hang fixed in the sky, neither rising nor setting, a permanent red lamp nailed to the heavens. And in the sky you might also be able to see Alpha Centauri A and B as 2 bright points of light, the brightest stars in your sky, far brighter than any star appears from Earth. Let us now broaden our view and look at the other nearby worlds that might, like Proxima b, harbour the conditions for life. Because while Proxima b is the closest, it is not the only candidate in our stellar neighbourhood, and some of these other worlds have properties that make them arguably more promising for habitability despite being farther away. The next candidate worth our attention is Ross 128b, orbiting a red dwarf star called Ross 128, approximately 11 light-years from Earth. This planet was discovered in November 2017 using the radial velocity method with the HARP spectrograph at the European Southern Observatory. Ross 128b has a minimum mass of about 1.35 Earth masses and orbits its star every 9.9 days at a distance of approximately 0.0496 AU. Its equilibrium temperature is estimated to fall somewhere between -60 degrees Celsius and +20 degrees Celsius, depending on assumptions about its atmosphere. This places it squarely within the habitable zone of its star. What makes Ross 128b particularly interesting, and in some ways more promising than Proxima b, is its host star. Ross 128 is a quiet red dwarf. Unlike Proxima Centauri, which is violently active with frequent and powerful flares, Ross 128 shows very little flare activity. This is enormously significant for habitability. A quiet star is far less likely to strip away a planet's atmosphere over billions of years. A quiet star bathes its planet in relatively steady, predictable levels of radiation, rather than unpredictable blasts of ultraviolet and X-ray energy. If Ross 128b has an atmosphere, it has had a much better chance of retaining it compared to a planet orbiting a violent flare star. This makes Ross 128b one of the best candidates for habitability among all known nearby exoplanets. The main disadvantage is distance. At 11 light-years, it is nearly 3 times farther than Proxima b. In absolute terms, that means roughly 104 trillion kilometers. But the qualitative advantages of a quiet host star may outweigh the additional distance in terms of actual habitability. Moving a bit farther out, we encounter Teegarden's star B, orbiting a tiny red dwarf called Teegarden's star, approximately 12.5 light-years from Earth. This planet was discovered in June 2019 using the Carmine spectrograph. Teegarden's star is classified as an M7-type red dwarf, one of the smallest and faintest types of stars known. Despite its diminutive size, it hosts at least 2 planets. Teegarden's star B has a minimum mass of approximately 1.05 Earth masses, very close to Earth's own mass, and orbits its star every 4.91 days. A second planet, Teegarden's star C, orbits farther out with a period of about 11.4 days. What makes Teegarden's star B noteworthy is that it has one of the highest Earth Similarity Index scores of any known exoplanet. The Earth Similarity Index is a numerical measure from 0 to 1 of how similar a planet's physical properties are to Earth's. While this index is a simplification and should not be overinterpreted, it provides a useful shorthand for identifying the most Earth-like worlds among the thousands of known exoplanets. Teegarden's star itself is very old, estimated at about 8 billion years, and is relatively quiet compared to more active flare stars. This combination of an Earth-mass planet in the habitable zone of a quiet old red dwarf makes Teegarden's star be one of the most intriguing targets for habitability studies. At a distance of about 40 light-years from Earth, we find 2 systems that have become centerpieces of modern exoplanet research. The first is Gliese 12, a red dwarf star that hosts a planet called Gliese 12b. This world was discovered in May 2024 using NASA's Transiting Exoplanet Survey satellite, known as TESS, and was confirmed with observations from the CHEOP spacecraft. Gliese 12b has a size comparable to Earth, with a radius of approximately 0.96 Earth radii, making it very close to Earth-sized. Its equilibrium temperature is estimated at approximately 42 degrees Celsius, which is warm but potentially habitable with the right atmosphere. It was described by scientists as not a bad place for life. The critical advantage of Gliese 12b is that it transits its star. This means that as it orbits, it periodically passes between its star and Earth, blocking a tiny fraction of the starlight. This geometric alignment is enormously valuable because it allows astronomers to use transit spectroscopy to study the planet's atmosphere. When starlight passes through the thin ring of atmosphere around the planet during a transit, certain wavelengths are absorbed by atmospheric gases. By analyzing which wavelengths are absorbed and by how much, scientists can determine the composition of the atmosphere. This is the technique that the James Webb Space Telescope uses to study exoplanet atmospheres, and Gliese 12b is considered an ideal target for such observations. It is the nearest transiting temperate Earth-sized planet found to date. The second system at roughly 40 light-years is the extraordinary TRAP-PIST, one system which may be the most remarkable planetary system discovered beyond our own. TRAP-PIST. One is an ultra-cool red dwarf star, classified as M8v, making it one of the smallest and coolest stars known to host planets. It has 7 Earth-sized planets orbiting it, the largest batch of Earth-sized planets ever found around a single star. The full system was announced by NASA on February 22, 2017, and it immediately captured the world's imagination. The planets are designated TRAP, PIST, 1b through H, and 3 of them, planets E, F, and G, orbit within the star's habitable zone. Among these, TRAP, PIST, 1e has received the most attention as a potentially habitable world. It orbits in the habitable zone where liquid water is theoretically possible on its surface. Its size and mass are very similar to Earth's, and critically, it transits its star, making it accessible to atmospheric characterization by JWST. All 7 T, R, APP, IST, 1 planets are thought to be tidally locked to their star, with one side permanently facing the star and one side in perpetual darkness. The James Webb Space Telescope has been studying the TRAP, PIST, 1 system, and the results released in 2025 have provided the most detailed look yet at these worlds. For the innermost planets, TRAP, PIST, 1b and c, the conclusions are sobering. These planets appear to be bare rocks without significant atmospheres. The intense radiation and flaring of their host star has likely stripped away any atmospheric gases these worlds may once have possessed. For TRAP, PIST, 1e, the results are more nuanced and still evolving. Based on analysis of 4 transits observed with Webb's NIR SPEC instrument, the researchers found that it is unlikely that TRAP, PIST, 1e has a thick atmosphere dominated by carbon dioxide. Like the atmospheres of Venus or Mars, the planet has almost certainly lost its primary atmosphere, the original hydrogen and helium envelope with which it may have formed, due to the star's flare activity. This was expected. However, the researchers also found that the data does not rule out the possibility of a thinner secondary atmosphere. There are hints, not yet confirmed, that the planet might have an atmosphere containing methane. A thin atmosphere with some greenhouse gases could potentially sustain liquid water on the surface, either as a global ocean or as a pool on the star-facing side surrounded by ice. The research team is careful to note that there are no direct parallels with our solar system. TRAP, PIST. 1 is a very different star from our Sun, and the planetary system around it is correspondingly different, challenging both observational and theoretical assumptions. 15 additional observations of TRAP, PIST, 1e are currently underway, using an innovative technique where the telescope observes planet B and planet E transiting back to back. Since planet B is confirmed to be a bare rock without an atmosphere, any signals detected during its transit can be attributed entirely to the star, providing a baseline. Any additional chemical signatures that appear only during planet E's transit can then be attributed to planet E's atmosphere. This clever approach helps separate the planet's signal from the star's inherent variability. The results from these additional observations have not yet been published, and the scientific community is waiting with intense anticipation. Beyond these key targets, there are several other notable candidates worth mentioning briefly. Gliese 667 cc, located about 22 light-years from Earth, has a minimum mass of at least 4.5 times Earth's, and orbits within the habitable zone of a star in a triple star system. Lu-10 b, also known as GJ273b, sits about 12.4 light-years away, with a minimum mass of about 2.89 Earth masses in the habitable zone of a red dwarf. Wolf 1061c, approximately 14 light-years away, is a super-Earth in the habitable zone of its star. Each of these worlds has its own set of intriguing properties and challenges, and each adds to the growing catalogue of potentially habitable real estate in our cosmic neighbourhood. But they all share one common trait. With Proxima b, they orbit red dwarf stars. This is not coincidence. It is a consequence of both the overwhelming prevalence of red dwarfs and the fact that planets in the habitable zones of red dwarfs orbit close to their stars, making them easier to detect via radial velocity and transit methods. Now we must confront, in full and unflinching detail, the staggering distance that separates us from even the nearest of these worlds. I presented some of these numbers at the beginning, but But now it is time to truly sit with them, to explore them from every angle, and to understand why this distance represents perhaps the greatest challenge our species has ever contemplated. 4.24 light-years. That is the distance to Proxima Centauri b. Let me convert that number into units that a human being can theoretically relate to. 4.24 light-years is approximately 40.14 trillion kilometers. It is approximately 24.94 trillion miles. These are pure numbers, and they are so large that they carry no intuitive weight. So let us use comparisons. The distance from Earth to the Moon is about 384,400 kilometers. To travel from Earth to Proxima Centauri, you would need to make the Earth-to-Moon trip approximately 104.4 million times. If you started today and made one round trip to the Moon every single day without ever stopping, it would take you approximately 285,000 years to accumulate enough trips to equal the distance to Proxima Centauri. The distance from Earth to the Sun is about 150 million kilometers, 1 astronomical unit. The distance to Proxima Centauri is approximately 268,000 astronomical units. To cover that distance, you would need to travel from Earth to the Sun and back approximately 134,000 times. The closest Mars ever gets to Earth is about 55 million kilometers. The distance to Proxima Centauri is roughly 730,000 times the closest Earth to Mars distance. If every Mars mission we have ever launched represented a single step on a journey to Proxima Centauri, we would need to launch 730,000 Mars missions, laid end to end, to bridge the gap. The distance from the Sun to Pluto is about 5.9 billion kilometers. The distance to Proxima Centauri is approximately 6,800 times the Sun to Pluto distance. Our entire solar system, from the Sun to Pluto and back, fits nearly 3,400 times into the gap between us and the nearest star. Now, let us think about travel time at various speeds. If you walked at a comfortable pace of 5 kilometers per hour and never stopped, not for sleep, not for food, not for rest, it would take you approximately 913 million years to reach Proxima Centauri. That is nearly 1 billion years. For context, 1 billion years ago, the most complex life on Earth was single-celled organisms. You would need to walk for a span of time equivalent to the period between the rise of the first multicellular life and the present day. If you drove a car at highway speed, 120 kilometers per hour, non-stop, it would take approximately 38 million years. The dinosaurs went extinct 66 million years ago, so you would arrive at Proxima Centauri about 28 million years before the asteroid that killed the dinosaurs even hit Earth, if you measured backward from today. If you flew in a commercial airplane at 900 kilometers per hour, the trip would take approximately 5.1 million years. 5 million years ago, the ancestors of modern humans were just beginning to diverge from the ancestors of chimpanzees. If you traveled at the speed of a rifled bullet, about 4,320 kilometers per hour, the journey would take roughly 1.06 million years. 1 million years ago, Homo erectus was wandering the plains of Africa. If you moved at the orbital speed of the International Space Station, roughly 27,600 kilometers per hour, it would take approximately 166,000 years. 166,000 years ago, anatomically modern Homo sapiens had only recently evolved, and they were still hundreds of thousands of years away from inventing agriculture. If you traveled at the speed of the Apollo 10 capsule during its return from the Moon, the fastest any human being has ever traveled at approximately 39,897 kilometers per hour, the trip would take about 115,000 years. If you could maintain the launch speed of New Horizons, the fastest spacecraft launch speed ever achieved at about 58,500 kilometers per hour, the journey would take roughly 78,000 years. New Horizons has slowed considerably since its launch due to the Sun's gravitational pull, and its current speed is about 51,500 kilometers per hour, which would stretch the trip to about 90,000 years. And then there is Voyager 1. At its current speed of approximately 61,200 kilometers per hour, or about 17 kilometers per second, the trip would take over 73,000 years. Voyager 1 has been traveling since 1977, and is still not one light day from Earth. A light day is about 25.9 billion kilometers, roughly 173 AU. Voyager 1 is at approximately 172.6 AU. After nearly half a century, it is just now approaching the distance that light covers in a single day, and we need it to cover a distance that light takes 4 years and 3 months to cross. On December 24, 2024, the Parker Solar Probe set the record for the fastest speed ever achieved by a human-made object, reaching approximately 692,000 kilometers per hour, or about 192 kilometers per second, during its closest approach to the Sun. This is a staggering speed. At this speed, you could fly from New York to Tokyo in about 75 seconds. But even at this record-breaking speed, if you could somehow sustain it continuously through open space, which you cannot, because the Parker Solar Probe only reaches this speed near the Sun due to the Sun's gravitational pull, the trip to Proxima Centauri would still take approximately 6,600 years. 6,600 years ago, human civilization was in its earliest stages. Writing had not been invented. The pyramids would not be built for another 2,000 years. And this is with the fastest speed any human object has ever achieved. These numbers paint a clear and sobering picture. With current technology, with every machine we have ever built, with every rocket we have ever launched, interstellar travel is not merely difficult. It is, for all practical purposes, impossible. Not theoretically impossible. The laws of physics do not forbid it. But practically, with the tools we have today, the distances are simply too vast, and our vehicles are simply too slow. And here we must talk about the fundamental reason our spacecraft are so slow relative to the interstellar distances, and that reason comes down to energy and the rocket equation. Every spacecraft humanity has launched uses chemical propulsion, either alone or in combination with gravity, assists from planets. Chemical rockets work by burning fuel to produce high-speed exhaust gases. Newton's third law, for every action there is an equal and opposite reaction, provides the thrust. The best chemical rockets, using liquid hydrogen and liquid oxygen, achieve an exhaust velocity of about 4.4 kilometers per second. That is the speed at which the burned fuel shoots out the back of the rocket. There is a fundamental equation in rocketry called the Tsiolkovsky rocket equation, and it governs the relationship between a rocket's exhaust velocity, the mass of its fuel, and the final speed the rocket can achieve. The key insight of this equation is that the fuel requirement grows exponentially with the desired speed. To double your final speed, you do not need to double your fuel. You need to square the fuel ratio. To triple it, you need to cube it. This exponential growth means that reaching very high speeds with chemical rockets requires absurd amounts of fuel. To reach just 1% of the speed of light, about 3,000 kilometers per second, with a chemical rocket, you would need a fuel mass so large it would dwarf the mass of the observable universe. It is not an engineering problem. It is a mathematical impossibility. Chemical rockets are designed for maneuvering within the solar system. They are fundamentally, physically, irreducibly incapable of interstellar travel. This is why scientists and engineers have explored alternative propulsion concepts, each with its own promise and its own set of staggering challenges. Ion drives, or electric propulsion, use electric fields to accelerate ions of a gas like xenon to high speeds. The exhaust velocity is much higher than chemical rockets, roughly 20 to 50 kilometers per second, which makes them far more fuel efficient. Ion drives are already in use. NASA's Dawn mission used ion propulsion to reach the asteroid Vesta and the dwarf planet Ceres. SpaceX's Starlink satellites use ion thrusters for station keeping. But ion drives produce extremely low thrust. They accelerate slowly. Over time, this slow, steady acceleration can build up significant speed for missions within the solar system. But for interstellar travel, the acceleration is far too low, and the journey would still take many thousands of years. Nuclear thermal propulsion uses a nuclear reactor to heat a propellant, usually hydrogen, to extreme temperatures, expelling it as thrust. The exhaust velocity is roughly double that of chemical rockets, about 8 to 9 kilometers per second. This technology was successfully tested by NASA during the NERVA program in the 1960s and 1970s. And the program was cancelled for budgetary and political reasons, not because the technology failed. There has been a recent revival of interest, with NASA and DARPA collaborating on the Draco program to test a nuclear thermal engine in space. But even with nuclear thermal propulsion, the improvement over chemical rockets is not nearly enough. Trip times to Proxima Centauri might be reduced from 73,000 years to perhaps 40 to 50,000 years, still vastly insufficient for any practical mission. Nuclear pulse propulsion is a much more radical concept. Originally studied as Project Orion in the late 1950s and 1960s, the idea was to propel a spacecraft by detonating small nuclear bombs behind it. A massive pusher plate at the back of the spacecraft would absorb the blast and convert it into thrust. This is not science fiction. It was a serious program, funded by DARPA and studied by some of the most brilliant physicists of the 20th century, including Freeman Dyson. Theoretical calculations showed that nuclear pulse propulsion could potentially accelerate a very large spacecraft, weighing thousands of tons, to 3 to 5% of the speed of light. At 5% of light speed, about 15,000 kilometers per second, the trip to Proxima Centauri would take roughly 85 years. That is within the span of a long human lifetime. It is the first concept we have discussed that brings interstellar travel into a time frame that a human being could theoretically survive. But Project Orion was never built, and there are profound reasons why. The 1963 Partial Nuclear Test Ban Treaty, which prohibited nuclear explosions in the atmosphere and in outer space, effectively killed the project. There were also massive concerns about radioactive contamination during launch from Earth's surface. The cost would have been astronomical, likely trillions of dollars in today's money, and the political will to build a spacecraft propelled by nuclear explosions simply did not exist during the Cold War or at any time since. A successor concept, Project Daedalus, was studied by the British Interplanetary Society from 1973 to 1978. Daedalus proposed using nuclear fusion micro-explosions rather than fission bombs. Small pellets of deuterium and helium-3 would be ignited by electron beams, creating a series of controlled fusion blasts that would propel an unmanned probe to about 12% of the speed of light. At this speed, the probe could reach Barnard's star, about 6 light-years away, in approximately 50 years. A more modern follow-up, Project Icarus, was studied from 2009 to 2014. Both Daedalus and Icarus remain purely theoretical. The core challenge is that we still cannot achieve controlled nuclear fusion on Earth, let alone miniaturize it for spacecraft propulsion. The ITER experimental fusion reactor in France has been under construction for decades and is not expected to produce full power until the early 2030s at the earliest. Private fusion companies have made progress, but net energy positive fusion remains elusive. Without mastering fusion on the ground, building a fusion-powered starship is out of reach. Antimatter propulsion represents the theoretical pinnacle of what is possible. When matter meets antimatter, they annihilate each other completely, converting 100% of their combined mass into energy, according to Einstein's E = mc². This is the most energy-dense reaction known to physics. The exhaust velocity of an antimatter rocket could theoretically approach the speed of light. A few kilograms of antimatter, if it could be produced, stored and controlled, would release enough energy to send a probe to another star system within a human lifetime. But the practical obstacles are almost comically insurmountable. All of humanity's particle accelerators combined produce only nanograms of antimatter per year, the total amount of antimatter ever produced by the human race, across all experiments in all particle physics laboratories worldwide, would not release enough energy to boil a cup of coffee. The cost of producing antimatter is estimated at roughly $62.5 trillion per gram. And storing antimatter is a nightmare, because it annihilates instantly on contact with any normal matter. It must be held in magnetic traps, which can contain only tiny amounts for limited times. To fuel an interstellar mission, you would need kilograms or tons of antimatter. We are not close to this capability. We are not even in the same universe of capability. Antimatter propulsion is real physics, but is currently so far from practical realization that it belongs to the very distant future, if it is ever achievable at all. The most promising near-term concept for an interstellar probe, and the one that received the most serious attention and funding in recent years, is laser sail propulsion, exemplified by the Breakthrough Starshot project. Announced in April 2016, just months before the discovery of Proxima b, Breakthrough Starshot was funded by billionaire Yuri Milner with support from the late physicist Stephen Hawking and Mark Zuckerberg. The concept is elegant in its simplicity. Instead of carrying fuel, which is the fundamental limitation of rocket-based propulsion, you eliminate the need for onboard propellant entirely. Instead, you build a massive laser array on Earth and use it to push a light sail. The plan envisions a fleet of tiny, ultra-lightweight probes called nanocraft, each weighing only a few grams. Each nanocraft would be attached to a light sail a few meters in diameter, made of an ultra-thin, highly reflective material. A ground-based laser array with a combined power of approximately 100 gigawatts would fire a concentrated beam of light at each sail, accelerating it to approximately 20% of the speed of light, about 60,000 kilometers per second, within just minutes of launch. At this speed, the trip to Alpha Centauri would take approximately 20 years. Data transmitted back via an onboard laser would take an additional 4.24 years to reach Earth, meaning the total time from launch to data return would be roughly 24 years. This is, on paper, the first truly viable concept for sending a human-made object to another star system within a single generation. It does not require exotic physics. It does not require antimatter. It does not require fusion. It uses lasers, which we understand well, and light sails, which have been demonstrated in space. But the engineering challenges are so enormous that they border on the fantastical. First, the laser array. 100 gigawatts is a truly staggering amount of power. For context, the total electricity generating capacity of the entire United States is roughly 1,200 gigawatts. The proposed laser array would consume roughly 8% of America's total power output. The most powerful continuous lasers currently in existence operate in the kilowatt range, a factor of 100 million short of what breakthrough Starshot requires. Building a phased laser array with 100 gigawatts of coherent, focusable power is an engineering challenge unlike anything humanity has attempted. Second, beam focusing. The laser must remain focused on a sail that is only a few meters wide as it accelerates to 60,000 kilometers per second and moves millions of kilometers away from the laser array within minutes. The precision required is almost unimaginable. Diffraction and atmospheric distortion would spread the beam, requiring adaptive optics on a scale far beyond current technology. Third, sail material. The sail must be ultra-thin and lightweight enough to be accelerated to 20% of light speed by the laser, but it must also survive the immense energy flux of 100 gigawatts concentrated on a few square meters. Current materials would simply vaporize. Researchers have been exploring nanoscale metamaterials, including membranes with billions of nanoscale holes that could improve reflectivity while reducing mass. But these are still in the early research phase. Fourth, the instruments. Each nanocraft must carry a camera, a power source, a navigation system, and a communication laser, all weighing just a few grams combined. Building functional scientific instruments at this mass is at the extreme edge of nanotechnology and microelectronics. The instruments must also survive decades in the harsh radiation environment of interstellar space. Fifth, the interstellar medium. At 20% of the speed of light, even the incredibly sparse atoms of hydrogen gas in interstellar space become a serious threat. Each hydrogen atom would impact the sail with enormous kinetic energy, equivalent to being bombarded by cosmic rays. Over a 20-year journey, the cumulative damage could be significant. Dust grains, even microscopic ones, would hit with the energy of small bombs. The nanocraft must either survive these impacts or be launched in large enough numbers that sufficient probes survive the journey despite attrition. Sixth, and this is perhaps the most overlooked challenge, deceleration. A laser sail is accelerated from behind. There is no laser at the destination to slow it down. A breakthrough Starshot nanocraft would fly past the Proxima Centauri system at 20% of the speed of light. The entire star system would be traversed in a matter of hours. The probe would have only a brief window, perhaps hours at most, to take photographs and gather data during its flyby. There would be no orbiting, no hovering, no second chance. It would scream past at 60,000 kilometers per second and keep going, forever, into the void beyond. And now, the most sobering update of all regarding breakthrough Starshot. According to reports published in September 2025, the project was placed on hold indefinitely. Funding had largely stopped. The multi-institutional meetings that had been driving the research ceased. and the future of the project became uncertain. It was reported that approximately $4.5 million had been spent on research. For a project of this ambition, that is a very small amount of money, and the quiet shelving of breakthrough starshot underscores a painful reality. Even the most promising concept for interstellar travel faces enormous headwinds, not only in physics and engineering, but in funding, political will, and institutional commitment. The dream of sending a probe to another star remains just that, a dream, albeit one grounded in real physics and serious science. Let us now consider what an actual interstellar journey would face, beyond just the challenge of propulsion, because getting a spacecraft up to speed is only the beginning of the problems. The space between the stars is not benign. It is a gauntlet of hazards that any spacecraft must survive for decades or centuries. Cosmic rays permeate interstellar space. These are high-energy particles, mostly protons and helium nuclei, that have been accelerated to enormous velocities by supernovae, active galactic nuclei, and other energetic astrophysical events. Within our solar system, the sun's magnetic field and solar wind create a protective bubble called the heliosphere that deflects many lower-energy cosmic rays. But once a spacecraft leaves the heliosphere, as Voyager 1 did in 2012, it is exposed to the full brunt of the galactic cosmic ray environment. For electronic equipment, cosmic rays can cause bit flips, memory corruption, and hardware damage. For biological tissue, they increase cancer risk and cause cellular damage. A crewed interstellar mission would require massive shielding, potentially meters of material, to protect its inhabitants, adding enormous weight and complicating propulsion requirements. At relativistic speeds, the interstellar medium itself becomes a radiation hazard. Hydrogen atoms that are stationary relative to the galaxy become, from the spacecraft's reference frame, a stream of high-energy particles hitting the front of the spacecraft at a significant fraction of the speed of light. At 10% of light speed, the kinetic energy of each impacting hydrogen atom is comparable to that of a cosmic ray particle. At 20%, it is even worse. A spacecraft would essentially be flying into a constant hail of radiation, requiring a forward shield. Dust is another serious threat. Interstellar dust grains are typically micrometers in size, far smaller than grains of sand. They are sparse, but they are there. At ordinary speeds, they are harmless. At relativistic speeds, they are lethal. A dust grain weighing a microgram, striking a spacecraft at 10% of the speed of light, would release kinetic energy equivalent to a small explosive charge. At 20% of light speed, the energy quadruples. Over a journey of 20 or more years, a spacecraft would encounter many such grains. Without a forward shield or some form of active protection, the cumulative damage could be catastrophic. For a tiny nanocraft like those envisioned by Breakthrough Starshot, a single grain impact could be mission-ending. Navigation over interstellar distances requires extraordinary precision. A spacecraft heading for Proxima Centauri must aim not at where the star is now, but at where it will be years or decades in the future, accounting for both the star's motion through space and the spacecraft's trajectory. Even tiny angular errors compound over trillions of kilometers. The spacecraft must carry autonomous navigation systems, likely based on star trackers, that identify specific patterns of stars and calculate position, because there will be no GPS and no ground-based navigation assistance. Communication delays of years make real-time guidance from Earth impossible. Communication itself is a major challenge. The inverse square law dictates that signal strength drops with the square of the distance. At 4.24 light-years, a radio signal is approximately 10 to the power of 13, or 10 trillion times weaker than it would be at 1 astronomical unit. Receiving data from a tiny probe at interstellar distances would require either an extremely powerful onboard transmitter, which adds mass and power requirements, or enormous receiving arrays on Earth, far larger than anything currently in operation. Even the Deep Space Network, NASA's array of giant radio antennas used to communicate with Voyager and other deep space missions, would struggle to detect a signal from a gram-scale probe at Proxima Centauri. And then there is the deceleration problem, which we touched on earlier, but which deserves further emphasis because it is one of the most underappreciated challenges in interstellar mission design. Most propulsion concepts that can actually get a spacecraft to interstellar speeds are one-directional. They accelerate the spacecraft, but they provide no means to slow it down at the destination. A laser sail is pushed from behind and has no brake. A nuclear pulse vehicle would need to carry enough fuel for both acceleration and deceleration, roughly doubling the fuel requirement and the mission complexity. Without deceleration, any interstellar mission is a flyby, a brief glimpse of the target system as the spacecraft screams past at thousands or tens of thousands of kilometers per second. Orbiting a planet, landing on a surface, or conducting long-duration observations would require the ability to shed an enormous amount of kinetic energy, and this remains an unsolved problem for all currently proposed interstellar missions. Now, let us turn from the challenge of getting there to the tools we are currently using to study these worlds from afar. Because even though we cannot yet visit the nearest potentially habitable planets, we can learn a remarkable amount about them using the most advanced observatories ever built. The James Webb Space Telescope, launched on December 25, 2021, is the most powerful space observatory in history. Its 6.5-meter primary mirror, made of 18 hexagonal gold-plated beryllium segments, and its suite of infrared instruments, including NIR-SPEC, MIRI, NIRCam, and NIRISS, make it uniquely capable of studying exoplanet atmospheres. JWST operates at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth, where a sun shield the size of a tennis court keeps its instruments at operating temperatures below 50 Kelvin, cold enough to detect the faint infrared signatures of distant worlds. The telescope's achievements in exoplanet science have already been historic. In 2022, it made the first unequivocal detection of carbon dioxide in the atmosphere of an exoplanet, WASP-39b, a hot Jupiter. It has detected the strongest evidence yet for an atmosphere on a rocky exoplanet, 55 Cancriae, a scorching lava world that was described as being like a wet lava ball, and it has been conducting the most detailed study ever undertaken of the TRAP-PIST-1 system, slowly building up data on each planet's atmospheric properties through repeated transit observations. But JWST has limitations that are important to understand. It cannot study the atmosphere of Proxima Centauri because Proxima b does not transit its star as seen from Earth. Transit spectroscopy, the method JWST uses to analyze exoplanet atmospheres, requires the planet to pass between its star and the observer. Without this geometric alignment, the technique cannot be applied. Proxima b, despite being the closest potentially habitable exoplanet, is inaccessible to JWST's most powerful atmospheric characterization technique. Even for transiting planets, detecting the atmosphere of an Earth-sized world is at the very edge of JWST's capabilities. The atmospheric signal from a small rocky planet is incredibly faint, and it requires multiple transits, sometimes dozens, to build up a strong enough signal to draw conclusions. Stellar contamination is a serious complication, especially for active stars like TRAP-PIST-1, whose spots, flares, and other surface features can produce signals that mimic or mask atmospheric signatures. The research on TRAP-PIST-1e demonstrates this challenge. 4 transits have been analyzed so far, and while certain atmospheric compositions like a thick CO2 atmosphere have been ruled unlikely, definitive confirmation of an atmosphere requires more data. The 15 additional observations currently underway will help, but the final answer may not come quickly. JWST also operates only in infrared wavelengths. It cannot observe invisible light, or ultraviolet, which limits certain types of atmospheric analysis. Some atmospheric gases, like ozone, have their strongest spectral features at wavelengths JWST cannot access. For a comprehensive characterization of a potentially habitable exoplanet's atmosphere, observations across multiple wavelength ranges would be ideal. This is why the future of exoplanet science depends on the next generation of telescopes, both on the ground and in space. On the ground, 3 giant telescopes are under development that will dwarf anything currently in existence. The European Southern Observatory's Extremely Large Telescope, or ELT, currently under construction in the Atacama Desert of Chile, will have a primary mirror 39 meters in diameter. For comparison, the largest optical telescopes currently in operation have mirrors about 8 to 10 meters across. The LT will have roughly 13 times the light collecting area of the largest existing telescopes, and will be equipped with advanced adaptive optics systems that can correct for atmospheric distortion in real time. It is expected to achieve first light in the late 2020s. The 30-meter telescope and the Giant Magellan Telescope are also under development, with 30-meter and 25-meter class mirrors respectively. These giant ground-based telescopes may be able to directly detect light from nearby exoplanets, separating the faint glow of the planet from the overwhelming brightness of its host star, using coronagraphs and other starlight suppression techniques. This would be transformative. Instead of relying on transit spectroscopy, which requires geometric alignment and is limited to certain wavelengths, direct imaging would allow astronomers to study the reflected light or thermal emission of a planet regardless of its orbital orientation. This means that even non-transiting planets like Proxima Centauri b could potentially be characterized. In space, several missions are planned or proposed that will advance our understanding of nearby habitable worlds. Plato, an ESA mission planned for launch around 2026, is designed to find and characterize Earth-like planets in the habitable zones of Sun-like stars, using the transit method, with a particular focus on bright, nearby stars. Ariel, another ESA mission planned for launch around 2029, is dedicated to studying exoplanet atmospheres through transit spectroscopy, building a systematic survey of atmospheric compositions across a wide range of planet types. The most ambitious proposed future mission is NASA's Habitable Worlds Observatory, or HOO. This concept, which is in the early planning and design phase, envisions a large space telescope specifically designed to directly image Earth-like planets around the nearest 25 or so Sun-like stars. Using an advanced coronagraph to block starlight, HOO would search for signs of habitability and potentially biosignatures, chemical indicators of life such as oxygen, ozone, water vapor, and methane in the atmospheres of these worlds. If funded and built, HOO could launch as early as the 2040s, though the timeline remains uncertain. It represents the logical next step in our quest to characterize habitable worlds. We have found them. We are beginning to study their atmospheres. The next step is to directly photograph them and search for the chemical fingerprints of life. Now, let us step back and take in the full panorama of what we have learned. We have traveled from the surface of Earth outward into the cosmos, scaling the vast distances between stars. We have met the closest star to our Sun, Proxima Centauri, a violent little red dwarf, invisible to the naked eye. We have examined its planet, Proxima Centauri b, a roughly Earth mass world in the habitable zone, discovered in 2016 through the painstaking measurement of a stellar wobble barely faster than a walking pace. We have explored what we know and do not know about this planet: its mass, its orbit, its temperature, its likely tidal locking, the terrifying flare activity of its host star, and the profound mystery of whether it has an atmosphere. We have met the other candidates: Ross 128b, orbiting a quiet star, Teegarden star b with its Earth-like mass, Gliese 12b that transits its star, and the extraordinary TRAP-PIST, one system with its 7 Earth-sized worlds where JWST is right now working to unravel the secrets of Planet E. We have confronted the distance, not as an abstract number, but as a living, breathing obstacle. 40 trillion kilometers of void, 73,000 years at Voyager speed, 6,600 years even at the fastest speed any human object has ever achieved. We have examined every propulsion concept humanity has devised, from chemical rockets that are mathematically incapable of the journey, through nuclear pulse propulsion that was killed by politics, to laser sails that were shelved for lack of funding. And we have looked at the tools we are using to study these worlds from afar: the magnificent James Webb Space Telescope, and the even more powerful observatories being planned for the coming decades. What emerges from all of this is a paradox so profound it can keep you awake at night. The nearest potentially habitable world is, cosmically speaking, right next door. It orbits the literal closest star to our Sun. If the Milky Way galaxy were the size of the continental United States, the distance from our Sun to Proxima Centauri would be roughly the width of a single grain of sand. And yet, that grain of sand represents a gulf so vast that our fastest machines would need thousands of years to cross it. The universe has placed a potentially habitable planet tantalizingly close and simultaneously impossibly far. This paradox teaches us something important about the cosmos and our place within it. The universe is not scaled to human dimensions. It was not designed for human convenience. The distances between stars are not obstacles waiting to be overcome by clever engineering. They are fundamental features of the universe's architecture, consequences of the physical laws that govern the size and spacing of stars, the expansion of space, and the finite speed of light. When we talk about reaching the nearest habitable world, we are not talking about a problem like flying across the Atlantic or landing on the moon. Challenges that were daunting but ultimately solvable with existing physics and a few decades of engineering. We are talking about a challenge that may require new physics, centuries of technological development, and a civilization-level commitment that has no precedent in human history. But this realization, rather than being cause for despair, should fill us with a particular kind of awe. Because despite all of these obstacles, despite the crushing distances and the inadequacy of our current technology, we know more about the nearest potentially habitable planet than any generation of humans before us could have imagined. Just 30 years ago, we had not confirmed the existence of a single planet beyond our solar system. Today, we know of more than 5,700. We know the mass of Proxima Centauri b to within a few percent. We know its orbital period to a precision of less than a minute. We know the temperature and spectral type and flare behavior of its host star in extraordinary detail. And right now, as you listen to this, the most powerful telescope ever launched is studying the atmosphere of a potentially habitable world 40 light-years away, looking for the chemical fingerprints that might tell us whether liquid water could exist on its surface. In 1903, the Wright brothers flew a motorized aircraft for 12 seconds, covering 37 meters, barely the length of a tennis court. 66 years later, in 1969, human beings walked on the moon, 384,000 kilometers away. In 1977, Voyager 1 was launched, and it is now over 25 billion kilometers from Earth in interstellar space. In 1995, we confirmed the first planet around a sun-like star. In 2016, we found a potentially habitable planet orbiting the nearest star. In 2022, the James Webb Space Telescope began revealing the atmospheres of distant worlds. The pace of discovery is breathtaking. Each generation has accomplished what the previous generation thought was impossible. But there is a difference between the challenges our species has overcome in the past and the challenge of interstellar travel. Every previous great journey, from the first ocean crossings to the Apollo missions, involved distances and speeds that were fundamentally accessible with existing or near-future technology. The Pacific Ocean is large, but a canoe can cross it. The moon is far, but a chemical rocket can reach it. Interstellar distances are not just quantitatively larger, they are qualitatively different. They require speed increases of a factor of 1,000 or more beyond what we have achieved, energy sources we do not yet possess, materials we have not yet invented, and mission durations that exceed the lifespan of not just individuals but civilizations. This does not mean it is impossible. It means it is hard in a way that nothing else has been hard. And it means that the first step is not building a starship. The first step is what we are doing right now, studying these worlds from afar, characterizing their atmospheres, understanding their climates, determining which ones are genuinely habitable and which are dead rocks in the right orbit, because there is no point in launching a 73,000-year mission to a world that turns out to have no atmosphere. The James Webb Space Telescope, the Extremely Large Telescope, the Habitable Worlds Observatory, these are not substitutes for interstellar travel. They are prerequisites for it. They are the reconnaissance that any wise civilization would conduct before committing to the most audacious journey in its history.